The second of the conics that we're studying is ellipses. And I really like all the conics, but ellipses are a very cool way to figure out how all of this is coming together. Because again, what we're trying to do is figure out what's the reason that an ellipse forms. Why is that happening the way that it does, and understanding the geometry so that we know why those are formed. And on Friday, you got some basics, but I wanted to come back to the formulas here. The key to knowing, am I going to have a horizontal or vertical ellipse? Because again, we are not going to talk about rotating these. That would require trig along with what we're doing, and we just want the basics of conics. So we're just going to have either horizontal or vertical. And the key is, where is the biggest denominator? Because the biggest denominator, only with ellipses, is going to be the indicator of, hey, if it's under x squared, this is a horizontal ellipse. If it's under y squared, then it's a vertical ellipse. And that's how we know which way to go with these. So we were at one that was called extra example. Here we go. And this one takes a step a little bit further. As we look at our objectives, we don't see complete the square to get a standard form equation for an ellipse. That's not what any of that says, but it does say write equations for ellipses and translate an ellipse. And it says prove that the graph of the equation is an ellipse and find its vertices and foci. And some people pronounce it foci, but a lot of books go with foci. So I look at that and I realize, well, it's not a parabola because it has both an x squared and a y squared. And as it sits right now, not sure whether or not it's going to have an x squared plus a y squared in there or not, but that's what I would be going for because we're supposed to prove this is an ellipse. And if it's an ellipse, what we want to do is have that x minus h squared plus y minus k squared equals 1. And right now, because I haven't completed the square yet on this problem, I don't know whether or not it's going to be an a squared here or a b squared here. But that's the look I need to get. Because if I have that nice formula with my h and k and a and b, then I can figure everything out. So prove that the graph is an ellipse and find its vertices and foci. Well, the first thing I'd have to do is realize x stuff needs to be grouped together, y stuff needs to be grouped together, and then I need a 1 on the other side. But let me work on the x squared and y squared stuff first. So 9x squared minus 36x, those two need to be grouped together. And then I have the plus 25y squared plus 50y. I didn't leave myself enough space writing that over there. And I do realize I'm going to need the number on the other side. This is not, it's very rare that they end up being perfect squares right off the bat and everything's set for you. So I'm going to add the 164 to both sides. All right, one step. We've got x's together, y's together, and a number on the other side. But I need to know, how do I complete the square? How do I get a perfect square trinomial so that I can factor it as a binomial squared? So I'm looking at 9x squared minus 36x, my first group, and I realize, well, a 9 can come out of both of those. Because here's the deal. We can't complete the square if there's a number other than 1 in front of the squared term. And then I look at my y squareds. And I notice there's a 25 that would come out of both of those. Now, the next step here, if you were with me first semester, I didn't show you this step in first semester. What we did in first semester was we moved all the numbers over to complete the square, because that helps you when you're dealing with fractions to not get lost in the process of completing the square. If you had Mr. Bloom, you've probably already done completing the square this way. Because here's the deal. I can't move both the 9 and the 25 over and make this in a form that I could complete the square. So what I have to do is think, well, if I don't pay any attention to this 9, what number would do the job here? And if I don't pay any attention to this 25, what number would do the job here? and then work with what I have. So I'm still using my little b over 2 squared formula to figure out this number. I ignore the 9. Negative 4. Negative 4 divided by 2 is negative 2, and negative 2 squared is 4. So I'm going to have to add 4. But then I realize I'm not just adding 4 to the left side, because I have this 9, this awkward 9 out here. And 9 times 4 would be 36. So I just added 36 to the left-hand side. I'm going to have to add 36 to the right-hand side as well. Do the same thing for the y's. Ignore the 25 for a minute. B over 2 squared. 2 divided by 2 is 1, and 1 squared is 1. But I didn't just add 1 to the left-hand side, because it has to be 25 times 1. So there's a little bit more to think about when we have ellipses and hyperbolas that we're going to be talking about to complete the square. But now this is great, because this is 9 times the quantity x minus 2 squared plus 25 times the quantity y plus 1 squared equals 164 plus 36 is 200. 200 plus 25 is 225. Getting there. Now we have our binomial squareds. Rats. Got this 9 and this 25, and that's not a 1. And that's where our focus needs to be. That has to be a 1 over there. So we're going to have to divide all of these by 225. And we'll think about what happens. So 225, if you think of it as if it were $2.25, you realize, oh yeah, there's 9 quarters in 225. So this will be x minus 2 squared over 25 plus 25 over 225. Well, that would reduce to 1 over 9. Now we've got it. So the extra piece for completing the square is remembering that you had a number outside the parentheses that was factored out to begin with, but that's going to change what you have added to the left-hand side. And you have to remember that for the right-hand side, because we still have to keep it balanced. Oh, we're almost done. Now it says we had proof that the graph of an equation is an ellipse. This is the proof right here. This is an algebraic proof that shows this is the standard form that we have for this. Pretty obviously it's an ellipse. I notice I have x squared, y squared, and a plus in between, and that was part of the definition of an ellipse and how it comes to be. So now I'm supposed to figure out where the vertices and the foci are at. So this takes on that, well, which way is it going? I mean, I can't tell them that if I don't know. And I notice, well, 25 is definitely bigger than 9. So this has to be my a squared. So if a squared is 25, that makes this a horizontal ellipse. And I'm going to make a little sketch so I can figure out these nice little points. So they have a couple of things they want us to tell them. So first things first, I need to know where the new center is at. And the new center is always going to be my h and k, so that will be positive 2 and negative 1. So I'll put a c there and 2, negative 1 to kind of help myself as I'm trying to figure out where all these points are that they need. Well, the vertices, if this is horizontal, are telling us how far to go out from the center. So if a squared is 25, then that means a is plus or minus 5. So I'm going to have to go 5 units in each direction horizontally from this point. And I realize, well, that's going to change it this way, right and left. So right now it's at 2. If I subtract 5 to go backwards, I'm at negative 3, negative 1. Again, it's at 2, and I have to go 5 units to the right. 2 plus 5 is 7. Negative 1. Now the foci are not something that are going to jump right out at us because it's not part of the formula. But I remember that if there's a plus in the formula for ellipses, that means if anything's missing, you have to have a minus in the formula. And that requires the use of both a squared and b squared, so I want to keep track of the fact that b is 3, since b squared is 9. But again, the big deal is this has a plus in its formula, so if something is missing, we have to use a minus to find it. C squared equals a squared minus b squared. So this will be c squared equals 25 minus 9. So what do we get? C squared is 16. So C would be, now again, that's not saying here are your foci. It's saying the foci are going to be 4 units away from the center horizontally because they have to be on that main axis. So we need to think same way that we did for the vertices. I'm at a 2 right now, but I have to go 4 units back to get to one of the foci. So 2 minus 4 would be negative 2. Negative 1. Y value is not changing. We're going right and left horizontally. And then if we have 2 plus 4, that'll give us 6. Negative 1 for the other pair. And there it is. Now I think we did everything. I don't want to scroll back up again here. We proved that it was an ellipse by putting it in that standard form. And we found the vertices and we found the foci. We're good to go. So we didn't have to graph it, but a sketch just makes that visual pop out in your brain and helps you figure out, yeah, horizontally, that's where I'm going to find my vertices and my foci. And then I'm going to find my covertices, my b values, vertically. Those will go up and down. And they did give us 2 names for these. I mentioned in the video on Friday. Not a lot of books even mention those 2 names. Semi-major axis for A and semi-minor axis for B. Yeah, you know, it's a step up in the vocab, but usually we refer to them as vertices and covertices when we find them. All right, so we're working on those applications. And this one says the reflective properties of an ellipse. Because of their shape, ellipses are used to make reflectors of sound, light, and other waves. If we rotate an ellipse in 3-dimensional space about its focal axis, the ellipse sweeps out what's called an ellipsoid of revolution. If we place a signal source at one focus of a reflective ellipsoid, the signal reflects off the elliptical surface to the other focus, as illustrated in this photo right here. This property is used to make mirrors for optical equipment and to study aircraft noise in wind tunnels. So if you live down by the airport, or if you pay attention to the news, it seems like every year there are complaints from the people that live in the area about how noisy all the planes are. So one of the things they do is they try to reduce that noise, either by putting up barriers. You know, the airport has to pay for some pretty big fences for people that live next to the airport, or they figure out how to make them quieter. And that's a part of this. But there's a very cool, it's always amazing to me that this has been around for as many years as it has. There's another very cool option here. It's a James Bond option, and it's about spying. Because if you have an elliptical room that's built that way with an ellipsoid of revolution, and you stand at one focus of the room, and you have somebody else at the other focus trying to get somebody to say something, you can hear what they're saying. And it's called a whisper gallery, because if it's audible to you, even if it's a whisper, you can hear it at the other focus. So whispering galleries in architecture, ceilings in the shape of an ellipsoid, are used to create whispering galleries. A person whispering at one focus can be heard across the room by a person at the other focus. An ellipsoid is part of the design of the Texas State Capitol. A hand clap made in the center of the main vestibule at the focus of the ellipsoid bounces off the inner elliptical dome, passes through the other focus, bounces off the dome a second time, and returns to the person as a distinct echo. So they can hear the little echo when they're standing at that point. But more importantly, It did. It used to be used for spying in a lot of countries, where you stand at the other focus, you have somebody placed at the other one, and as they're talking, you can listen in on what their conversation is. All right, so if the ellipse at the White House, which by the way is not inside, so it's not for spying, it's outside. So if the ellipse at the White House is 616 feet long and 528 feet wide, what is its equation? So the first thing I would want to see is, well, is it supposed to be horizontal? Is it supposed to be vertical? What's going on? And I see that the 616, the bigger number, is horizontal. Now, we didn't get a placement from them of, we want to think of the coordinates as centered at, so we can just do this centered at 0, 0, because again, if they don't give us that information, we get to place it wherever we want to. So with a horizontal major axis, we would want that one. X squared over A squared gives us that horizontal axis. Again, it's about the placement of the larger denominator. So when it's under x squared, it's horizontal. Well, A isn't 616 because A is how far out did they go from the center. And we're considering that to be 0, 0. So we're going to have to take 616 and divide it by 2 and get 308 for our A value. Same type of thinking here for B. We have to divide that by 2. 264, I hope. So that'll be 264 squared. And this is why I said this is the first one we'd probably want a calculator for. I don't think many people are going to do 308 squared in their noggin. Maybe you will. $94,864. And 264 squared. 69,696. So again, we didn't get any kind of direction from them about where the center should be. And when that happens, we definitely want to place it where it would be advantageous to us. And that would be with this center right here at 0, 0. And just dividing by 2 to get our A and our B, our semi-major and semi-minor axis. So ellipsoids, another really great use for these is in the healthcare profession. So ellipsoids are used in healthcare to avoid surgery and the treatment of kidney stones. Now, kidney stones are one of those things, men tend to get them more than women do. It's a buildup of calcium, and it creates basically a little hard stone. And almost all the time now, doctors will say, yes, I know it's painful, let me give you some medication, but you're just going to have to wait for it to pass. There are some people that, they take an ultrasound and they say, wow, that's a monster kidney stone. And they say, that's not going to come out on its own. We're going to have to figure out a way to break it up. So what they do is they don't use this much anymore. I'm going to tell you that even, when I was in the medical field, oh my gosh, has it been that long? 30 years ago, they were already using ultrasounds to break up kidney stones. They don't use a lithotripter very much anymore, but it's a process they can use. So an elliptical lithotripter emits underwater ultra-high frequency shock waves from one focus with the patient's kidney carefully positioned at the other focus. Very painful procedure because what they have to do is make sure they're hitting the kidney stone in the right spot. So at least to start off with, they won't give somebody a lot of pain meds because they want to know that they've actually hit the kidney stone and that it's breaking apart. So they go under the water and they use those UHF waves, and then they use the elliptical pool to move the person to exactly where the stone is. And once they do that, they pound it with these UHF waves and break it apart so that it's easier to pass. So they're showing us here in a 3D ellipsoid revolution how that all works. Like I said, usually they'll do it with ultrasounds now instead of the UHF shock waves. We're going to focus a lithotripter. The ellipse used to generate the ellipsoid of a lithotripter has a major axis of 12 feet and a minor axis of 5 feet. How far from the center are the foci? So, let's see what we know. Well, if the major axis is 12, what does that mean our A value is? 6. And if the minor axis is 5, what does that mean for B? 2.5. Half of it, major axis, minor axis, you break them in half to find A and B. How far from the center are the foci? Well, I wouldn't even need to write the equation for this ellipse. I just need to find out C. That's what I need. So I remember if it's an ellipse, ellipses have pluses in their formula. So if something is missing, we need to use a minus. It's like the Pythagorean theorem with subtraction inside it. So C squared will equal 6 squared minus 2.5 squared. And then we'll go ahead and take the square root. Oh, I should just punch it in so everybody can see that the math is right up to that point. So we'll have the square root of 29.75. Didn't really leave room for my plus or minus in there either. Trouble with spacing today. But in reality, they would want to know, in feet, in inches probably. So let's get this in feet. .454 feet. But again, they'd want to know a little bit closer than that, for goodness sake, so they'd probably change the .454 into inches. So let me subtract the 5 away and then multiply that by 12. So about 5.452 inches. So plus or minus 5 feet, 5.452 inches. And that should be the placement. So math involved in breaking up a kidney stone. All right, one more here. Another extra example. The moon travels about the Earth in an elliptical orbit with the Earth at one focus. That's really important to know. Let's put that little F right there for focus. The major axis has a length of 768,806 kilometers, and the minor axis has a length of 767,746 kilometers. Find the greatest and least distances from the Earth's center to the moon's center. All right, so here's the Earth. There's the moon, but the moon is going to be moving around. So when I look at it and I think about the path of the moon, I realize, well, this is going to be the shortest one right here. When the moon is over here, that'll be the shortest distance. They'll line up nice and straight. And the greatest distance is going to come from it being on the opposite side. Oh, come on, blue, behave. Nope, no blue this morning. So what I have to do is figure out, how do I find that? Well, let's see. If we can figure out the entire distance, which we already know there, 768,806, that gives us a chance to know what A is, because this is a horizontal axis given that this is larger than this one. So what I want to do is figure out first, since the focus is involved, where is the focus, you know? And that would be c squared equals a squared minus b squared again. But we do have to figure out a and b, and instead of trying to remember and flip those back all the time, we had 768,806. We would divide that by 2 to get a, and that is 384,403. I don't want to make you sit and watch me type that in, divided by 2. So there's A. And then B, semi-minor axis, 767,746 divided by 2, 383,873. So yeah, we got some math to do with those buggers. So c squared equals 384,403 squared minus 383,873 squared. Now I'll punch it in. Oofda. 407,186,280. And then we have to take the square root of that monster. $20,178.857. All right, so how are we going to figure out these distances? Well, we do know by dividing by 2 the length of A from each side. And if we take A and use that along with the distance for the focus, we'll be able to get the shortest and the greatest. And we just do it simply by subtraction. So if we want the least, let's start with that one, the least distance or the shortest distance. We're going to take our 384,403 for A, and we're going to subtract that focus off of there. And that comes out to and feel free to punch it in and check on me here, but like I said, rather than make you watch me do the subtraction, I'm just going to use my notes here this morning. 364,224.143 for the shortest distance. And for the longest distance, we have to take 388,403 and add our 20,178.857. And that comes out to 404,581.858. And each of these is in kilometers. So for the shortest distance, we take A minus our distance to the focus. Again, it makes sense when you look up the picture. I know green doesn't show up very well, but here's our focal distance right here. So if we take A and subtract that little green piece, then what we have left is the red piece that I have labeled shortest up there. And then if we take our A distance on this side and add that distance to the focus, well, now we're over there on the other side of the horizontal. So there they are. We had some good applications today. Elliptical, anytime you talk about ellipses, you're going to be talking about orbits. Those of you that are interested in becoming an astronaut, you know, those types of things have to be studied. Move that up a little bit. There we go. There is a part on one of these problems you're going to read where it asks you to find eccentricity. That's how that's pronounced. It looks like eccentricity, but like I said, we pronounce things weird in math sometimes. Eccentricity, ignore that. We're not going to study eccentricity. We're just going to do basics. And this doesn't require any graphing on it. Probably a couple of sketches, but not any graphing, so you shouldn't need graph paper for this one.